continue on here where we left up, pick up where we left off, if you will, as lecture 4, page 1 of something here. For us in the Hibbler text, this is going to be chapter 3. Chapter 3 is where we look at equilibrium of a particle. We're going to talk about what that means for us in a second, and then after chapter 4 we can look at equilibriums of structures, but here we're just going to look at equilibrium of a particle. And what we mean by this term equilibrium, that means the object is at rest, if originally at rest, or static. I'm in a hotel room today recording videos, and my puppy is she is whining occasionally. She hears people out in the hall, so if you hear that, I apologize. We're going to see if she's going to be hopefully quiet for us, and we'll continue on. So, what does this mean? That means we're dealing with Newton's first law we talked about previously, and that's the idea that if the net force acting on a particle or an object is equal to 0, that means that the acceleration of said particle is also going to be 0. So if the object is at rest, it will stay at rest until acted upon by an exterior force. And that means we're at equilibrium. We are at equilibrium until an exterior force causes a net force, and as a result, then will cause an acceleration or a change in motion. But until that net force occurs, the object is going to be static or in equilibrium. So the goal of this course, a statics course, is really trying to quantify or describe or identify situations where something is in equilibrium or static, or what forces are going to be required to maintain equilibrium. And that's really our focus over the next several weeks then. So what we're saying here is that we've been looking at resultant forces. And it's really our focus in chapter 2 forces, trying to find the resultant force. Chapter 3 is not a whole lot different. It's just simply that your resultant force must be 0 for equilibrium. So that means then that the resultant force, which we normally, I've written summation here, most of the time we probably won't, after chapter 2, it's pretty rare that we'll talk about write it in terms of resultant. Most of the time when we're referring to the resultant force, this is what we're referring to. The sum of all forces, which is what the resultant is. The sum of all forces is going to be 0. As we discussed before, the resultant then is going to have x, y, and now z components. Z. So if I take the sum of forces in x, y, and z, they're all going to add up to be 0, meaning if I add up all the forces in the x direction, they must be 0. If I add up all the forces in the y direction, they must be 0. And if I add up all the forces in the z direction, they must be 0. And basically what we're saying is we're going to equate, similar to equating coefficients. My statics professor used to tell us, he used to joke, statics is super simple because there's really only one equation, and that's true. This is really kind of the main equation. There are more than that, but you can see in 3 dimensions this equation splits out into 3 different equations. This one vector equation, when we look at the different components of that vector involved, we're saying if I add up the total forces, the net force vector must be 0. That means the force in all 3 directions must be 0. And in a 2D problem, this one goes away. I'm just dealing with x and y, which is what we'll start with. Now, We've mentioned up here earlier, chapter 3 is where we're focusing on equilibrium of a particle. That means we need to discuss, what does a particle mean? Oh, I found new pens, by the way. All right? So we're from Rose State College, so I found some nice Rose State College pens. If you want one, stop by. I've got a handful of them. I'm going to hoard some of them, though, because they actually write pretty good and they're pretty comfortable to use. So I think a few of these is going to get me through this whole course. What is a particle? A particle is any object that can be modeled as a concentrated point of mass. That's what I mean by particle. We'll understand a little more about what the significance of that is when we get into chapter 4. But for us right now, it just simply means that if I've got a former professor, a former colleague of mine, he used to call it a mutant potato. If you just draw some lump of mass and call it a mutant potato, let's say I apply 3 different forces to this mutant potato here, F1, F2, and F3 at arbitrary magnitudes and angles. If it's a particle, what I mean by that is it makes no difference as far as these forces are concerned, whether it's a mutant potato or any shape that you want, or if I have a single point representing that mass. The net result is the same. The size and shape, let's write that. That's important. What I'm about to say is actually very important. By the way, sometimes I'll write Z like this, sometimes I'll write Z like this, and they're both fine. This is kind of a cursive Z, just fair warning. You'll see that, especially if I'm writing words, I tend to write like this. If I'm writing in math, I tend to use that. Anyway, size and shape of a particle are irrelevant. I'm going to pause here. All right, we're back. Had to readjust a few things here, but we'll just keep continuing on. So we've defined the idea now of a particle. Let us define, we've used it before, mentioned the importance of a free body diagram, and we're going to continue. That's a very powerful tool we will continue to use throughout this course. Let's talk about what it is. We should have seen these in physics, hopefully, and again, we've seen us do a few of these already. A free body diagram is very simply a sketch showing, oh, you can't see that, I apologize. We're okay, Hazel. This is a sketch showing all forces acting. Let me see if I can get her to stop. I apologize. So free body diagrams. This is a simple sketch showing all forces acting on a system or part of a system. Hazel, we can't play right now. Daddy's busy recording videos. How do we draw a free body diagram? Again, we've seen these a little bit. Let's talk a little more about how we do these. Step number one, you want to isolate and draw a simple model of the system or part of the system of interest. What is it you're wanting to analyze? Draw a very simple diagram of it. Doesn't have to be real detailed if it's a free body diagram. If it's a particle, it can just simply be just a point. You don't even have to draw the full shape because, again, if we're treating as a particle, the size and shape do not necessarily matter. So if I'm drawing a free body diagram of something I can model as a particle, I can just simply draw it as a dot. That is perfectly okay. Then we want to add any angles, dimensions, or geometry needed. And then finally, we want to draw all forces acting on the system or part of the system. I cannot stress to you how important free body diagrams are. If you're just copying solutions from solutions manuals or some website, they are not going to stress to you probably the importance of how valuable a free body diagram is. I remember when I took statics, it was in a very large classroom, several hundred people. Our professor had an army of TAs that would do the grading for him, and he would tell his TAs, if the problem is 100% completely correct, that's fine. But if there's no free body diagram and there's a single mistake, it could be a negative sign, they were to give us 0, no partial credit whatsoever. If there's a free body diagram, they could be as liberal with partial credit and as generous as they wanted to be. If you made a simple mistake, it could be a simple number of points. But if there was no free body diagram, he was very clear. It is all or nothing, because basically if there's no free body diagram, you're basically doing a lot of steps, very important steps in your head, and he didn't want you to do that. Not to mention, as I mentioned in some of the early videos, it's vitally important that you can communicate accurately what you're trying to do as an engineer. Free body diagrams are a very simple way to communicate what forces you believe are at play on the system or part of the system that you're analyzing. So, with that in mind, you'll hear me use this phrase quite a bit, and you'll hear this phrase thrown around in a statics course a lot. The idea of apply equilibrium. When we say apply equilibrium or write equilibrium equations, what we are saying at that point is to sum all forces acting on a free body diagram, which that's FBD. That is a free body diagram. We're not going to write free body diagram out very often. We're just going to call it an FBD. To apply equilibrium means you're going to sum all forces acting on a free body diagram in X, Y, and Z, and set those sums equal to 0. You say if the sum of forces in the X is equal to 0, and the sum of forces in the Y are going to be equal to 0, and the sum of forces in the Z are equal to 0. I mentioned earlier, our statics instructor was very clear, if there's no free body diagram, there's no partial credits. And this is why, because it's so simple. If I can look at an object, if I can look at a diagram, then I go through and look, okay, well, what are the forces in the X direction? Add them all together. What are the forces in the Y direction? Add them all together. What are the forces in the Z direction? Add all of those together. It is very, very easy to do that, almost without error, if your free body diagram is correct. Even if your free body diagram is not correct, then I can be a lot more generous about my partial credit, because this is really what I'm grading, is what are your equations you're going to have sum of force equal to 0 is equal to then, and you're going to have maybe 5 or 6 different forces in the x direction. If I can look at your free body diagram, and then I can compare it to your forces in the x direction, I can say, oh, you missed this force, you accidentally applied it in the y direction, or whatever it is, and that's a lot easier to put partial credit on. But if I can't see it, then all I've got is a set of an equation and a bunch of terms in it, and it's probably not real clear where those are because you've probably just copied them off a solutions manual and they've skipped a bunch of steps. It's a little harder to give partial credit on those. Anyway, I'm going to stop this one here, and we'll start the next one.